in the last lesson we saw that sine of 200 is a number that's related to sine of another value. And from the last lesson we saw the 200 degrees somewhere over here. So the y-coordinate is the same, at least the negative of the y-coordinate of this point. And it turned out that this was a 20-degree angle. That was the reference angle. So sine of 200 and sine 20 are not the same number, but sine 200 is negative, sine 20 is positive, but otherwise they're like the same number. But we can go a little further now if we have a trig chart which has the values of sine, cosine, and tangent of angles between 0 and 90 degrees. And here's a trig chart, and as we can see, here's sine, and sine of 20 degrees is 0.3420. So with our trig chart, we can actually go this one step further. So if you have a trig chart and you have the ability to take an expression like this and convert it into an expression like this, where this number is less than 90, this might be a plus, might be a minus, depending on our quadrant, we can go further and get the sine, cosine, and tangent of any angle, integer angle. So the next big question is, where did all these values come from? Is there some way that we can calculate them? And that's what the next few lessons are going to take you through. There are a few values that are easier than others. For instance, if you take, I have here an equilateral triangle with side lengths of 1, and if I bisect it into two 30, 60, 90 triangles, these will each be a half, and if I use the Pythagorean theorem, I can find that this one is square root of 3 over 2. And then I can work out what sine, cosine, and tangent are of 30, 60, and 90, because sine 30 is opposite over hypotenuse, so that's a half, and sine 60 is the adjacent over the hypotenuse, which is radical, I meant hypotenuse, so it's radical 3 over 2. And cosine of 30 is adjacent over hypotenuse, which is radical 3 over 2. Here's the adjacent. And cosine of 60 is adjacent, which is a half now, over hypotenuse, which is 1/2. And while I'm at it, though I didn't mention it much so far, tangent is opposite over adjacent. So that's tan of 30 is 1/2 over 3 radical 2, over radical 3 over 2, which turns into 1/2 times 2 over radical 3, which is 1 over radical 3, which if you rationalize the denominator becomes radical 3 over 3. And tan 60 is going to be the reciprocal of that, the opposite over the adjacent, radical 3 over 2 over 1/2, which becomes radical 3. So that gets us a bunch of values, 6 of them. We can get some more values by looking at a square instead of an equilateral triangle and dividing it into two pieces. Now I have these two 45, 45, 90 triangles. This is square root of 2 by the Pythagorean theorem, and with that I can say sine of 45 is opposite over hypotenuse. I'll come to another page for that. The opposite was 1, the hypotenuse was 2, was radical 2. Cosine of 45, because now if I'm doing cosine of 45, the adjacent becomes 1, but the hypotenuse is still radical 2. So cosine of 45 is also radical 2 over 2. And tan 45, that's the easiest tangent value of all, because the opposite over the adjacent, they're the same number. So it's 1 over 1, or a tangent of 45 equals 1. So with this, we get sort of the 9 basic trig values that a lot of people memorize. You can see that the denominators for the sines and cosines are all 2's, and the numerators for sine goes up 1, square root of 2, square root of 3, and in cosine it goes down square root of 3, square root of 2, 1. One thing you might notice is that cosine 30 is the same thing as sine 60, and that's going to be true in general, that cosine of x is going to be sine of 90 minus x. Those two things will add up, and that's because if this is x and this is 90 minus x, then the cosine, I'll just the side that is opposite, or I should say adjacent to the x, is also the side that's opposite the 90 minus x. So for cosine adjacent over hypotenuse is b over c, but or cosine of x is b over c, but sine of 90 minus x is also b over c, because the adjacent to one angle is the opposite to the other angle that remains. Now, in the last lesson I mentioned about how tangent is not officially in the unit circle, but if this is cosine and this is sine and this down here is 1, because of similar triangles, sine theta over cosine theta is equal to whatever this is over 1. But we know that sine over cosine is tangent. So that makes this piece here tangent. It's no accident that it is a tangent line, or at least a segment that's tangent to what would be the whole circle. Now we've seen that cosine x is equal to sine of 90 minus x. And those two angles are complementary. And cosine, actually, the co stands for complementary. So here's a more complicated picture. Here's theta, and this is 90 minus theta. And as you can see, I have here's sine over here. It's not written in for some reason. And though cosine can be thought of as down here, if I draw this other triangle over here, cosine is also here, because this is a rectangle. And you can see that cosine is kind of like the sine of the 90 minus theta, the complementary, because this is the opposite. Its cosine up here is opposite the 90 minus theta. Now, if I draw in the tangent line, and then I continue the radius, and I draw another tangent line up here, and I continue the radius until those two things meet, there are a lot of triangles in this picture. Let me erase this. We can see them a little better. Now, here's theta. So this is sine theta. This is cosine theta. This is tangent theta. And this from here to here is a secant line that goes through the... So the hypotenuse of this red triangle, or of this larger triangle here, is known as the secant of theta. On the other hand, if I take the 90 minus theta here, this line here is the sine of the 90 minus theta, otherwise known as the cosine. This line here is called the cotangent. And the cotangent is the tangent of the complementary angle. And this large hypotenuse is known as the cosecant. So there are 6 things: sine, cosine, I'll write it this way: sine, tan, secant, cosine, cotan, cosecant. And those 6 things are related by something called the trig identities. And what I'm going to do is I'm going to take these triangles. There's 3 triangles. There's the red one. I'll make this medium-sized one blue. And this large one is going to be green. And if I take these triangles and put them side by side, one sine, cosine, the other one is blue. That blue triangle has 1 as its bottom side. This is tan. This is secant. And the green one, the large green one, if I flip it upside down, I do have like a theta up here. So I have 1 as this opposite side, and cotan as its adjacent side. One. And with these 3 triangles, they're all similar to each other, I can produce the 8 fundamental trig identities. And the 3 of them come from the Pythagorean theorem. So this is a right triangle, so cosine squared theta plus sine squared theta has to equal 1. This is also a right triangle, so 1 squared, which is 1, plus tangent squared theta has to equal secant squared theta. And this one here is a right triangle, so I could say cotan squared theta plus 1 squared, which is 1, is equal to cosecant squared theta. Cosecant is always the hypotenuse, so it's going to be the bigger one. It's going to be the one that's by itself in these 3 so-called Pythagorean identities. There are 5 more identities that we can get through similar triangles. So if I take the red and blue triangles, I can say that sine over cosine equals tan over 1, which is a very well-known. I'm not going to write the theta right now. If I take the red and blue again, but instead I use the secant, the hypotenuse, and the adjacent side, I could say secant over 1 is equal to 1 over cosine, which is another famous identity. If I take this green triangle and the red triangle, I could use similar triangles to say hypotenuse over opposite, or cosecant over 1 is equal to 1 over sine. Those 3 are known as the reciprocal identities. Oh, I'm sorry, not those 3. These 2 are. This is something else altogether. The third reciprocal identity comes from the green triangle. I could take the adjacent and the opposite, so cotan over 1, and compare it to the blue triangle is equal to 1 over tan. Sorry, so these 3 are the reciprocal identities. These 3 are the Pythagorean identities, and this one's sort of a special separate identity. And I could also, if I take the red and the green, I could say cosine over sine, the adjacent and the opposite, is equal to cotan over 1. Okay, this is looking pretty messy. Here it is, nice. These are the 8 fundamental trig identities. 3 of them are from Pythagorean theorem. 3 of them are called the reciprocal identities because it's something equals 1 over something else. And the other 2 just come from similar triangles also. Actually, once you have this one, you can combine it with this one to say cotan is 1 over tan theta, which is 1 over sine theta over cosine. So you could actually get to this last one 2 different ways. One way directly from the triangles, and another way by combining these 2.